Why is it so gosh darn satisfying to watch things blow up in slow motion? That is not the topic of today's video. Not at all. Today, I'd like to talk to you all about quantum tunneling. My name is the number 12, and this is Nerd Candy. Greetings, everybody, and welcome to episode 1 out of at least one of Nerd Candy, featuring quantum tunneling. Quantum tunneling is what happens when a particle pushes through a barrier with a higher potential rating than the particle's own energy. Hey! In English, please! Well, alright, if it must be simplified for you, I got a series of graphs. Alright, so what we've got right here is a very simplified diagram of a potential barrier setup in quantum mechanics. First of all, some introductions. This guy right here is the particle. The x-axis is the position of the particle, and as you can see, the potential barrier goes from 0 to L along the x-axis. And on the y-axis, we instead have V, which stands for potential energy. And I should also mention that the particle itself comes with E, a preset energy value, which, as you can see in this setup, is greater than the potential barrier, whose potential energy is V0. Now here in this case, as I'm sure you can probably imagine, the particle could just slide right on through that potential barrier because its energy is greater than V0, so there's really no trouble. Well, of course you made it, you silly little particle. That was the easy part. Now, while it looks like nothing really happened while I was going over the barrier, a little bit of a change did occur in the wave function of the particle. This isn't super critical to this video, but it'll still be useful for padding out the videos, explaining what's really going on at the elementary level. Wave functions are basically equations that tell you what a particle is doing, and they're usually graphed as sinusoids, that is, a sine or a cosine curve. Now, the wave function of that particle we just witnessed changes on the potential barrier. First off, you see this initial wave function. See those peaks and valleys, and the spaces between them? Well, now we come to the barrier zone and things get slowed down because the particle's net energy has gone down to E minus V0. Once you get past it though, oh, well, look, there it is, good as new. But that's not quantum tunneling. That's just what potential barriers do to interrupt particle motion. What do you make of this now? Here, the particle's energy is clearly less than the barrier, so what happens? It just gets rejected every time, right? You might be thinking of the model of classical physics. Classical physics has a particle do this. So yes, if we set it to the classical laws of physics, the particle will bounce off the barrier and its wave function becomes a reflected wave, equal to the initial wave but in the opposite direction. But it's called quantum tunneling, so it doesn't obey classical physics now, does it? This is where things... Hey, particle, where are you going? This is the good part! Man, and I've only got 6.3 quadrillion more where that came from too. But no matter, this is better understood with the wave function anyway. Once again, the first part of the wave is a basic sinusoid. The big difference comes when it reaches the barrier that starts at x equals 0. Most of the time, it gets reflected back with the same motion but in the opposite direction. But if it hits the barrier just right, the particle can penetrate the barrier by becoming a negative exponential, that is, a graph similar to e to the negative x. It loses energy but still manages to squeeze in. It's important to note that what you're seeing on the graph isn't the energy going down, it's the probability going down. As you might expect, the deeper into the barrier you go, the less likely it is the particle can survive. But if it does make it, what you get on the other side is a tiny sinusoid. And again, the size of it, or rather the amplitude, is not indicative of a lower energy, but how unlikely it is to make it there. And the fact is, it should be a lot smaller. Also take note that the wavelength is still the same as it was when we started. In case you were wondering, here's how to calculate the probability of tunneling. I'm not going to go very deep into it, but a few things to note. The barrier's length is a much bigger factor than the barrier's height. That sinh stands for hyperbolic sine, and also unless you have a barrier less than a nanometer across and the particle's energy is only off by 1 electron volt or less, you'll have a better chance of winning the Mega Millions. Now you're probably wondering how this can even happen at all. How can electrons just violate classical mechanics like that? Well, the simplest answer is Heisenberg's uncertainty principle. Because we cannot know the exact position and the exact momentum of a particle at any given time, the wave function is not really an exact definition of this is what particle is doing, this is what particle is. Another thing you might be wondering is, why should I care? What good does this do in the real world? And to that I say, what kind of hecking rock have you been living under? Come on, everybody knows about quantum tunneling. Just watch and learn. Hello, random bystander. Tell me, what is your favorite aspect of quantum tunneling?
What?
Quantum tunneling. What's your favorite aspect of quantum tunneling?
I don't know what quantum tunneling is.
What? What do you mean you don't know? It's quantum tunneling.
Quantum tunneling? Quantum of
Quantum
solace?
tunneling.
Like a tunnel for trains?
Quantum tunneling! Well, that didn't turn out the way I'd hoped. It did make me look like more of a psychopath than I really am in the real life, though. Just, by a slight margin. So that's something. Alright, all joking aside, let's take a look at why quantum tunneling really is important in the real world. This is Leon Esaki, or as his friends called him, Leo. He was born in 1925 and is actually still alive as of this recording on December 8th, 2018. Pretty impressive for a man who had to live through the bombing of Tokyo by the United States as a young adult. His achievements include being a top employee at Tokyo Tsushinkogyo, which later turned into Sony, and his co-development of superlattices in semiconductors. But the big one was what he came up with in 1957. After co-discovering quantum tunneling in the first place, he and his colleagues immediately worked to exploit it with this, the tunneling diode. But wait, what did that idiot say? You'll have a better chance at winning the Mega Millions? Well, here's the thing. These are electrons. They're tiny. Tunnel diodes contain quadrillions of electrons. So while that graph I showed simplified how it could happen to one electron, in reality the scene looks more like... And so, because of all that action, we still get billions of electrons to make the tunnel every second. What can the electrons do? Well, depending on how the device is oriented, they can act as an oscillator or an amplifier. The device is usually made of germanium, gallium, or silicon, basically semiconductor materials. So in this case, the barrier that the electrons tunnel through is the energy gap between the highest occupied ground energy level and the lowest unoccupied excited energy level. If it's facing forward, the electrons tunnel through a very narrow junction barrier, which then conduct electricity and align with poles from the positive side of the circuit, and you get a current going. However, if you increase the voltage, you end up losing the current, because inserting more potential energy to the current makes the electrons tunnel less and less often, like I demonstrated. This is really useful because with an adjustable voltage, you can control the current flow as you like it. If it's facing backward, the electrons behave as rectifiers, which change AC alternating current to DC direct current. DC only flows in one direction, so this is another way tunneling can give us control over how electrical devices work. Now, tunnel diodes are kind of special. Because they have low capacitance, they function in the microwaves, which most diodes and transistors don't get to do.
However, due to the disappointingly low power level, they are not widely used in many appliances.
Tunnel diodes are very resistant to radiation, which means they can be commonly used on space missions. Tell me, do you like pretty pictures? Like this one?
Or this one? Or this one? Wait, one more. Or this one. You like them? Because if you don't like them, you lot need to get off my planet so you can personally appreciate the other planets like you should. Picnic. So, yes, you can thank tunnel diodes for controlling the current flow on most space probes. Another lovely feature is that the tunnel diode has longevity, like really, really good longevity. Some of the devices Esaki built himself back in the early 1960s are still operational. And I am very happy to report that Leo Esaki did in fact receive the Nobel Prize in 1973 for this, which he invented in 1957. Interesting. Quantum tunneling also occurs naturally on the universal level. Inside a star, the reason that nuclear fusion can occur, and therefore the reason stars shine, is because loose particles inside the superheated center of stars have that small probability of overcoming the Coulomb barrier and joining two nuclei together, which fuses them into heavier elements and radiates energy. The Coulomb barrier happens in every star because of repulsive forces between protons. Because they're both positively charged, they don't want to be near each other, so that becomes the potential barrier. The strong nuclear force, one of the four fundamental forces, helps protons tunnel through this barrier and join other protons to become helium, and neutrons may or may not follow suit. And the reason this is related to energy is because energy is related to mass with E equals mc squared. So when the protons join together, they also generate energy, which keeps the star's power alive so it can radiate heat from its surface. Quantum tunneling also works in the reverse way, in radioactive decay. In this case, the particles break away from the atom structure by tunneling backward through that potential barrier. And of course, this leads to the energy being split apart as well. This is important for development of life on planets, because radioactive decay, the release of particles and energy outward, can provide an energy source for neighboring planets. If the source is relatively constant over a large period of time, like with our Sun, then there will be a wider habitable zone for a planet to reside in that may achieve life. And so, in conclusion, sometimes a violation of the classical laws of physics can really be beneficial toward creating a healthy universe, as well as helpful for achieving new breakthroughs for the human race. Please don't take that statement out of context. Well, that wraps up episode 1 of Nerd Candy. Hope you enjoyed, and, naturally, with this being my first time doing this, I have no idea how to end this video. Here's my cat, Sparky, doing cat things. Sleeping. That's the most cat thing of all. Other cat things. He doesn't like his water bowl anymore.
Sparky like the camera? Sparky likes the camera?
That's what they're gonna name
Get the want it? Huh? Sparky. Hey, Spark. Sunky. I'd rather check out the billiards. Quantum tunneling is what happens when a Pokemon. Jeez. Okay, so what we've got right here is a very simplified setup of a potential barium. Barium. Okay then. Man, I've only got 6.3. Read the number. The number is. I have a script. Read it, dude. Come on. What can the electrons do? Well, depending on how the device is oriented, they can act as an oscillator or an amplifier. They're usually made of germanium, gallium, or silicon. Wait, shoot. I should probably specify what's made of germanium, gallium, or silicon? Not the electrons.